We will get started at 11:05. If you have any questions, let me know. You can write in the chat as well before we get started. We have about 1 more minute. Any questions?
Nope.
All right.
No, sir.
All right.
Oh yeah, I do have a question.
Okay.
So, are you still going to reopen that quiz
It
for
should
Sunday?
still be
Or
open. Is it not open?
no? I tried doing it, but it was closed. It said it had closed at 11 on Monday.
On Monday? Let me look. It should have still been open.
Yeah, it was still closed because I meant to say something about that too.
Okay, let me look. Oh, yep, it is still closed. Okay. I'm going to extend it until Sunday,
All
11:59
right.
p.m. All right. All right, you should be good to go now. And I just do want to remind everyone, you can access the class site from Moodle through here. And using the class site, you can get all of our resources. I will upload the videos for the lectures probably today. And we'll go from there. If you have any questions, just let me know. And that quiz should be open now. If you have issues getting to it again, let me know. All right. As I'm going through these slides, if you have any questions for the materials, just speak up or write it in the chat if you don't want to speak up. All right. Today we are covering data representation, binary and hexadecimal. We'll talk about how to convert from binary to decimal, how to convert from decimal to hexadecimal, decimal, and vice versa, all the way on down. Hopefully by the end of this, you know how and you can practice it. We will have a lab on Friday and an individual assignment due Sunday. Okay. And I understand with these conversions, you obviously can go on the internet and find a conversion calculator, make it real simple. You can do it in 5 minutes. But this is something important for you all if you're interested in pursuing a career in computing or you're interested in converting from binary in general. It's not very difficult. Once you get the hang of it, it comes fairly easily. So I would encourage you to actually learn how to do it because why not? You know, it helps in the future and it helps now in this class. So let's get started. Can everybody see the slide?
Yes.
All right, cool.
Yes.
Perfect.
Yes.
All right. So binary. Why binary? Binary is base 2. There are two symbols, either a 0 or 1. And whereas with decimal, it's base 10. We have 10 possible digits, 0 through 9. So binary, we have 0, 1. There's only 2 digits. Each individual digit is referred to as a bit. Okay, so one binary digit is equivalent to 1 bit. And the reason that we use binary in computing is because historically, computers worked off of individual little light bulbs. And I actually want to look up the name of those CPU. What are they called? I forget the term of them now, but historically or in the past, they worked off of light bulbs. Either the light bulb was on or they were off. Very simple, binary, a 1 or 0, on or off. Now we have individual little, I forget the term or the name of them, but they're little tiny bit of devices or components on a CPU that either have electrical charge or they don't. So a 1 or a 0. And that's how CPUs work. They run off of 1s and 0s. It's very easy to translate binary into a physical medium. And it's easy to translate binary from a program to hardware. And so the CPU can interpret that. Even in storage and memory, we use binary for addressing. So if we want to address into a storage system or RAM, we'll use a binary address. And we'll talk about that in a little bit. All right, so a bit versus a byte. 1 byte is equivalent to 8 bits. And you see here, 1 kilobyte is equivalent to 1,032 bytes. 1 megabyte is equivalent to 1,032 kilobytes, so on and so forth with gigabytes and terabytes. We also have petabytes beyond a terabyte, which is 1,032 terabytes. And then we have, more and more down the line. Interesting fact, I believe across the internet, about 20 terabytes of data is generated every day. So that's interesting. And that's why there's huge interest in big data analytics, trying to find patterns in people's behaviors, computers' behaviors, and trying to use those patterns for marketing or targeted ads, things of that nature. Google is real big in visual analytics and big data analytics. All right, data representation. So we represent all data in memory or storage as bits. So you ever heard of a 32-bit system or 64-bit system? All it means is the amount of memory addresses you can have. So a 32-bit system, you have 32-bit memory addresses. So each one of those bits, you can have a 0 or 1, right? It's base 2. So we can have 2 to the possible 32 unique memory addresses, which is roughly 4 million. Well, as you can imagine, that's not a lot. It allows up to 4 gigs of memory, but like I said last time, 4 gigs of memory is becoming not enough for modern day operating system, modern day programs. If you open, I don't know, 20 Chrome tabs, even 8 gigabytes of memory may not be enough. Well, with 64-bit systems, it allows up to 2 to the 64, which is roughly 18 quintillion unique memory addresses. The amount of RAM that those systems can hold is quite significant, and this is 18 quintillion, the actual number of 2 to the 64 right here. I wanted you to get an idea of what that looks like. And so, as I said previously in the last lecture, with more RAM, you can load more programs that you're running. For example, PowerPoint is currently running in RAM on my computer. I have some Google Chrome tabs open. Those are in RAM. I have Word open. I have this Zoom session open. All of those programs are loading into RAM once I start running them. With more RAM, that means I can load more programs into memory, right? If I don't have a lot of RAM, that means my system has to swap from the storage, my hard drive, solid state drive, to RAM. And it's constantly doing that process. That would significantly slow down a PC. So when a person's PC is running slowly, there's usually two things you can look at. Either the CPU is slow and there's not much you can do unless you replace the CPU, or they don't have enough RAM on their system. And usually you can update the amount of RAM even on laptops. All right, so let's talk about converting binary to decimal. So here's a binary number. Again, that's 8 digits, right? 1, 2, 3, 4, 5, 6, 7, 8, which is also called a byte, or it's called an octet when we talk about MAC addresses and IP addresses. Octet, octa is 8. That's how that translates. All right. So first, I just wrote the number out, the binary number out, 00101011. Okay. And for binary, you always read right to left. And in computing, indexes, so this is the first index, second index, third, fourth, fifth, sixth, seventh, and eighth. With indexes, you always start at 0 in computing. So technically, this is 0, 1, 2, 3, 4, 5, 6, 7. Right? Those are the indexes of that binary number. So for each one of these binary numbers, again, it's base 2. So it's either 0 or 1. So what we do is we multiply each one of these numbers times 2 to whatever index it's at. And I wrote down what that equals. 2 to the 0 is not 2. It is not 0. It is 1. Okay? 2 to the 1 is 2. 2 to the 2 is 4, 8, 16, 32, 64, 128. And if you notice, each successive number is the previous number multiplied by 2. Okay? So to look at this, we do 0 times 128, 0 times 64, 1 times 32, 0 times 16, 1 times 8, 4 times 2, 0 times 4, 1 times 2, 1 times 1. Once you get all those products, you just add them up. So since these are zeros, we're not going to use those. This is a 1, so we bring that 32 down. This is a 0, we're not going to use that. This is a 1. This is a 0, we're not going to use that. This is a 1, and this is a 1. So 32 plus 8 plus 2 plus 1 is actually, it's actually 43, not 45. All right. Did everybody see how I got there?
Can you repeat it?
Certainly. All right. So what you do is you multiply each one of these digits times 2 to whatever index it's at. So 2 to the 0, because this is the 0 index. 2 to the 1, this is the 1 index. 2 to the 2, this is the 2 index. 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, and 2 to the 7. And I wrote out what those each equal. This equals 128, 64, 32, 16, 8, 4, 2, and 1. So now, 0 times 128 is obviously 0. 0 times 64 is obviously 0. 1 times 32 is 32. 0 times 16 is 0. 1 times 8 is 8. 0 times 4 is 0. 1 times 2 is 2. Then 1 times 1 is 1. Once you have all those products, you add those up. 32 plus 8 is 40. 40 plus 2 is 42. And 42 plus 1 is 43.
Yeah, I got it.
All right. I have another example as well. So here's another number. Separate these out. Multiply each one of these times the 2 to the index. Another way of looking at this, if there's a 0, you don't use it. So you're not going to use these. If there's a 1, you bring it down. So if there's a 1 here, you bring down 128. If there's a 1 here, you bring down 64. 1 here, you bring down 16. 1 here, you bring down 4. There's a 1 here, you bring down 2. You add up all these products, and you get 216. Did anybody?
It's
Go ahead.
the numbers that square, they always gonna be the same, like 1, 2, 4, 8.
Yes.
It could change.
It's always going to be the same. So, and you're always reading right to left as well, because the most significant bit is on the right, which is that 1. Also, if you look here, this rightmost bit, if it's a 0, you're going to have an even number. If that rightmost bit is a 1, you're going to have an odd number. Everybody get that?
Yeah.
Yes, sir.
All right. I want you all to try to convert this number right here. This is the first one. Let's just do the first one. I'll give you 5 minutes. So I'll give you until 11:25. You can jump in if you have questions.
I got 149.
All right. Did everybody, if you're still working, keep working. I'll let you know if that's right in a second. And for reference, I'll go back so you can see the different indexes and what they equal. This is not the number. All right, so the answer is 149. Did anybody get something different?
I got 149.
All right. Does anybody need me to go over those previous examples?
No, sir.
Well, I will continue. All right. So now we're going to convert from decimal to binary. Okay. So from decimal to binary, we put up all these indexes again, right? 2 to the 7, 2 to the 6, to the 5, to the 4, 3, 2, 1, and 0. And we're trying to convert this number, 241. All right. So now we start left to right for this conversion. So is 128 less than or equal to 241? Yes, it is. So we put a 1. Now we subtract 128 from 241. That's how I got 113. Is 64 less than or equal to 113? Yes. So I put a 1. Then I subtract 64 from 113. Is 32 less than or equal to 49? Yes. I put another 1. Subtract 32 from 49. Is 16 less than or equal to 17, which is 49 minus 32? Yes, it is. Put another 1. Then I subtract 16 from 17, I get the 1. Is 8 less than or equal to 1? No. So I'm going to put a 0. Is 4 less than or equal to 1? No. I'll put a 0. Is 2 less than or equal to 1? No. Put another 0. And then is 1 less than or equal to 1? Yes, it is. I put a 1 right here. You see how I got that? Or do you need me to run through that again?
Can you
No,
run
that
through it?
makes pretty sense.
Okay, I'll run through it again, and I have another example after this. So one more time. So we have all our positions, right? And these correspond to our indexes. So 8 bits, right? We have 1 byte. So this is position 0, 1, 2, 3, 4, 5, 6, and 7. There's 8 bits right here. Since we're trying to convert 241, all we do is subtract it if it's less than or equal to 241. So let's go through this. Is 128, which is the leftmost bit, less than or equal to 241? Yes, it is. We add a 1. Then we subtract 128 from 241 because we already used it. That's how I get 113 right here. So 64 is less than or equal to 113? Yes. Put another 1. Subtract 64 from 113. Now I have 49. 32 less than or equal to 49? Yes. Put a 1. Subtract 32 from 49. That's how I get 17. 16 less than or equal to 17? Yes. Put a 1. Subtract 16 from 17. And now I'm left with just 1. 8 is obviously not less than or equal to 1, so no. 4 is not less than or equal to 1, no. 2 is not less than or equal to 1. However, 1 is equal to 1. So yes, put a 1, and we're done. Everybody get that? I'm going to go to the next
Yeah.
example, a little bit different. It's an even number plus it's smaller. So is 128 less than or equal to 74? No.
No.
So we put a 0 right here. Is 64 less than or equal to 74? Yes. We put a 1. Is 32 less than or equal to 10? I got 10 from subtracting 64 from 74. No. Put a 0. Since we didn't use 32, we just carry this over. Is 16 less than or equal to 10? No. Again, we didn't use 16, so we carry this over again. Is 8 less than or equal to 10? Yes. We put a 1. Subtract 8 from 10. We get 2. Is 4 less than or equal to 2? No. We put a 0. Carry this over. 2 is equal to 2. So we use that, we put a 1, and we subtract 2 from 2, we are left with a 0. Well, 1 is not less than nor equal to 0, so we put a 0 right here, and this is our final binary number. Does that make sense?
Yes, sir.
All right. So now your turn. I want you to try to convert 89. There should be 8 bits when you're finished. I'll give you another 5 minutes, so 11:35, we'll keep going. When you get your final binary number, just write it in the chat. All right, that is correct. Anybody get something different? Do you need me to walk through it? If not, I'll continue. If you do have questions, just let me know. All right, so hexadecimal. Pretty simple. So hexadecimal is just 4 bits now, right? With 4 bits, there's a possible 16 different values. However, in computing, we don't want to use 10, 11, 12, 13, 14, 15, and 16 because technically 10 is 1, 0. 11 is 1, 1. We want individual digits to represent up to 16 values. And why they did this is to make large binary numbers more human readable. Right now we can convert, for example, up to 4 bits into 1 digit. So here, if we look right here, 0000 corresponds to 0 in decimal, and then in hexadecimal, it's also 0. However, 1111 in binary is 15 in decimal, but F in hexadecimal. So 0, 0, 1, 1, 2 is 2, 3 is 3, so on up to 9. However, 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and then 15 is F. Starting from 0 inclusively, that is 16 possible digits. And here is a table to show all of those. So here's the binary equivalent, the decimal equivalent, and the hexadecimal equivalent. Anybody have questions? I'll leave that up there for a few seconds so you can process that. All right, let's continue. All right, so now we convert binary to hex. Okay, now you see this long binary number. This is actually 16 different digits. So if we split that down the middle, that makes this 2 bytes. And since hexadecimal, we only use 4 bits at a time. So when we split this binary number into 4 bits, this is what we're left with. 1101, 0010, 0101, and 1010. Using that previous table that I showed, this is our decimal equivalent. And then this is the final hexadecimal equivalent and the final hexadecimal number. Pretty straightforward. That table makes it a lot easier. Here's another example. We split this into 4 bits, parts. Here's our decimal equivalent. And then finally our binary, our hexadecimal equivalent. Questions, comments, concerns?
Hold up, can you stay on this page real quick?
Yeah.
Hey, I got a question.
All right.
So on the can you go back to that chart with the that had like everything out there?
Yep.
So F is 15 or 16?
15.
Why? Because on the little other joint it says 16.
Did I have 16 on there? Yeah, let me fix that.
Yeah.
Thanks for catching that. That should be 15. Yeah. Everyone else good? All right, well, I'm going to keep going. Now, hex to binary, using that chart again, we separate this out to 4 bits. Here are their equivalents. And then here's the binary equivalent. We do this again. Well, that's the last example for that. Hex to binary. Next, I'll talk about the internet, just real quick, networking and how the internet works. So last class, I kind of talked about local area networks and what those are. Essentially, those are what it says, a local area network. So imagine your home network. You have your routers. You have your router coming from the wall, right? Your ISP connects into your router. Some of you might have a modem as well. All a modem does is convert one signal to Ethernet. It converts the coaxial cable, which is like the old cable, TV cable. It converts those signals into Ethernet for your router. That's all a modem does. It's a modulator. It converts that. So inside your home network, all these devices, so you might have your phone, your smartphone, your computer, your tablets, all connected through Wi-Fi. You might have a gaming system or a desktop PC connected through Ethernet. On your local area network, all these devices communicate with your router or one another using a MAC address. And a MAC address is a physical hardware address assigned by the manufacturer, okay? However, if you want to communicate, say this is your local computer, if you want to communicate with this web server over here, you're going to use something called an IP address. The reason we use an IP address is because IP addresses are routable across the internet. They're in between here, in this internet little cloud right here, there are many different routers that are interconnected. And those routers do what their name implies. They route. They route network traffic using IP addresses because the whole internet is organized into different domains, different IP domains, and those routers know where those domains are and are able to, hey, I have this IP address. I know that I need, in order to get to its final destination, whatever device is assigned to this IP address, there are different parts in that IP address that tells a router where it needs to go. And it learns over time where the best and most efficient path is. For example, this computer right here, if it's trying to reach this server, Google, it's going to connect to its, imagine this is a route, its local area network router. Right here, it's going to communicate with that router using the MAC address, right? It's going to send it using the MAC. Then this router is going to communicate with the ISP using the MAC, with the MAC, with the MAC, with the MAC. However, we know the final destination IP address, and these routers in between know how to translate between those MAC addresses and the IP addresses, and using that IP address, how to route to this final destination. All right. Local area network. And let's talk about how the MAC addresses and IP addresses are broken down. This is why we talked about binary previously. So MAC addresses are 48-bit unique addresses, all right, for each network interface card. As I said before, 8 bits is considered a byte, but also when it comes to addresses, called an octet, 8 bits. So the first octet, second octet, and third octet are broken down to the organizationally unique identifier. So each organization, whether it be Samsung, Asus, AMD, whatever it may be, Intel, they have a unique, organizationally unique identifier, right, for each one. And they may have several. And so their first 3 octets are for that unique identifier to the organization. Right? So each network interface card, Ethernet or Wi-Fi, have that organization's unique identifier as the first 24 bits. The last 24 bits is specific to that network interface card. So my question for you all is, given that the last 24 bits are unique for that network interface card, how many different network interface cards can one organization have? We have 24 bits, so how many different unique addresses can there be? Anybody want to take a stab at it? If not, I'm just going to tell you. It would be 2 to the 24. right? If we have 24 bits, that means there's 2 to the 24 different possibilities and different unique IP addresses, or MAC addresses, I'm sorry.
You said 224?
2 to the power of 24. Right? There's 24 bits, so that means there's, for each bit, you have 2 possible outcomes, a 0 or 1. So if you have 24 bits, that's 2 to the power of 24.
Ah, okay.
Mhm. And if you ever see a MAC address written out, it's typically written in hexadecimal format. So the first 3, again, the first 3 octets are for the organization. The last 3 octets are for the network interface card. Remember, in hex, each digit is 4 bits. So this is 8 bits, this is 8 bits, this is 8 bits, 8 bits, 8 bits, 8 bits. All right, so now before we end class, let's talk about IP addresses. So the most common IP address is an Internet Protocol version 4 address, IPv4. What these are 32-bit addresses, typically written in decimal dot notation, broken down into 4 octets. So 192.168.1.1. So each one of these numbers are 8 bits. Right? And we did this previously. So this would be 8 bits, this would be 8 bits. This 1 is still 8 bits. It would just be 00000001. Same thing for this one. It's 00000001. With 32 bits, we have 2 to the 32 possible unique IP addresses, which is roughly 4 million. But as you can imagine, there are way more than 4 million people on the planet. Or is it 4 billion? It's 4 billion, sorry, with a B. There are roughly 4 billion addresses, but again, even with that number, there are more than 4 billion people on the planet. And although everyone doesn't have a device, possibly, most people do have at least one device, and a lot of people have way more than one device. Cell phone, laptop could have 2 IP addresses associated with it. Tablets, anything, any internet connected device. Alexa would have an IP address. A web camera would have an IP address. All those different IP addresses. So as you can imagine, we've exhausted most of those IP addresses. So we came up with something called network address translation, which translates public IP addresses to private IP addresses. Public IP addresses are assigned by worldwide organizations to specific companies. Right? So for example, your ISP would have a public IP address, or several. Google has a public IP address because they're so large. Then within inside your local area networks, each device would have a private IP address, okay? And this is an example of a private IP address. Your router would be responsible for translating between that public and that private IP address, right? And that's just a way of conserving the public IP addresses so that we can delegate them out. If you have a Windows PC and you want to see your IP address, open a command prompt and type in ipconfig, and you'll see it. So just to, an advancement or innovation of IP version 4 is IP version 6, which instead of 32 bits, we have now 128 bits addresses. So that's 2 to the 128, which is a far, far larger number than 4 billion. And hopefully with that many bits, we'll never run out of IP addresses, but it could be. However, IP version 6 isn't as popular because many devices don't recognize it yet. Because there are a lot of older devices on the internet that don't even have the capabilities of processing IP version 6. But that is it for today. Anybody have any questions? Comments or concerns? All right, if
Nope.
not, I'm sorry, what?
Say no.
If you do have any questions, you can email me. That will be available. Just let me know. Again, I will try to upload these to the website. The recordings, the slides are already on the website. But if that's it, no questions, that'll do it for class today. And I got you, Teron.
And then you